Okay, so this is going to be video 4 for the 114 practice final exam version B, starting with question 16 and looking at still at the topic of torque. So we've got a uniform beam of mass 20 kilograms and of length 1 meter is attached to the hinge on the wall of a restaurant or a recognizable coffee shop on the Ave. A cord is attached to the beam and is attached to the wall, making an angle of 30 degrees with the beam. The cord keeps the beam perpendicular to the wall. If the breaking tension of the cord is 620 newtons, how large can the mass of the sign be without breaking the cord? Okay, so torque problem. So the sort of just to recognize, so this is the beam in the question. This is the cord. We know it can withstand a tension of 620 newtons, and we want to know how large the mass of the sign can be. So the beam is sort of the object of interest. So I would sort of recommend, as I said, drawing an extended free body diagram for the beam and identifying the forces that are on the beam. So there is a, well, let's draw our pivot point. So I'm just going to choose sort of a natural pivot at the wall. And there is a force that does act here. But what's nice is for the context of torque, the force that's applied at that point doesn't exert any torque on the beam because it is applied at the pivot. So I'm only looking at forces external to that particular point, or in a sense that are not acting at the pivot. So there is a weight force since the beam has a mass that acts. Assume if it's a uniform beam, it does say uniform. So that means that the center of mass is at its geometric center. So I'll draw a weight force acting here. And that's the weight force on the beam by the earth. And that's acting at 0.5 meters from the pivot. Then at 0.6 meters we've got a tension force acting at a 30-degree angle. And we know its maximum value is 620 newtons. That's the tension on the beam by the cord. And then there'll be another force, so let's do a different color. And that's acting over here. And it's sort of the tension by the sign, or you can probably would be a tension force or some sort of force. Maybe I'll just leave it as just an open force that's on the beam by the sign, which sort of would be equivalent to the mass of the sign times g. It would be equivalent to its weight, but the sign is not exerting a weight force on the beam. It's exerting some other type of force. If it's held up by a string, or some sort of rope or cord or chain, it would be a tension force. But since it's not really specified, we'll just leave it as a force. But since the sign is at rest, the upward force on the sign must be equal to its weight force. Therefore, third law of force per the sign is pulling down on the beam with a force equivalent to its weight. So now we have to figure out how big that mass can be if we're at the sort of breaking tension of the if we assume at the maximum tension force in the cord. So about this pivot point, the weight force would like to cause the beam to rotate in a clockwise direction. The sign would like to go in a clockwise direction, and the tension is going to have to compete with those two to get a counterclockwise torque. Hopefully I said those things correctly. So clockwise torque, I'm not sure if I said tension there or not. Clockwise torque by the weight, clockwise torque by the sign, and a counterclockwise torque. I'm not sure if torque by the tension force. I'm not sure if I said torque or tension. So I'll set the clockwise torques equal to sort of the counterclockwise torques, such that the net torque is 0. So the net torque has to be 0. So the magnitude of the torque by the tension has to be equal to the magnitude of the two clockwise torques, weight BE plus the magnitude of the torque by the sign. And that hopefully will set up a problem to solve for the mass of the sign. So the tension, this will be 620 newtons. Here I would recommend decomposing the tension force into two components, finding F perp. So this would be F perp, or basically maybe I'll write this tension perp, since it is a tension force, but it's the power of the force is perpendicular to its position vector. This is 30 degrees. So this time we are using a sine function. So 620 times the sine of 30 degrees times 0.6 meters. I want to run out of room here, so let's drag this a little bit to the left. That will give you the torque there, and then this will be 20. I'll just drop out the units just so I have enough room to write. So that's the weight of the beam itself, 20 times g, so mass times g, and it's acting half a meter from the pivot point, and then the tension, or the sine, is acting at the mass of the sine times again 9.8 times its distance of 1 meter from the pivot point. Again, I don't have to include an angle there because the angle is 90 degrees between the force and the position vector, so sine of 90 is 1. So the only unknown we have in this expression is ms. So I'll go ahead and then sort of work out our algebra to solve for this particular quantity. So I'm just going to do this in Excel. I'm doing my sine of 30 is a half times 0.6, and then I've got 20 times 9.8 times 0.5. So if I bring that across, so we sort of be left with sort of if I'm not ignoring my units for a second, equals ms times 1, and then the sine has to be oh sorry, I'm missing the 9.8. So 88 divided by 9.8 should give us the mass of the sine, 8.98 kgs. So yeah, sorry, I know I skipped a few steps there, but hopefully you can follow the steps to solve for ms, just doing your algebra correctly, and that will give you choice D as the correct answer. Okay, so let's move on to 17, getting into sort of balance and sort of critical angle, sort of middle of chapter 8. A box in the shape of an equilateral triangle is sitting on a horizontal floor. The center of mass is at the geometric center at point P. And what is the critical angle for this object? So this is for the critical angle from chapter 8. So we're doing critical angle is the tan inverse of sort of a half t, but I'll put the 2 down here, divided by h, where t is the track width and h is the distance to the center of gravity from the bottom. So I'll highlight that here on the diagram. This will be equivalent to h, this will be equivalent to t, and we have basically, from this point, that's sort of most of the physics piece done, but we really have to get h. We don't have h. We need to write h in terms of t in order to basically solve this problem. So from this point on, we're going to sort of going to challenge with trig. So it is an equilateral triangle, so that's sort of the key piece to the question. So that means all sides are the same length and all angles are the same, so 60-degree angles, which is why, in a sense, this is split into 30 and 30, which is why P is at the geometric center. So if I sort of concentrate on the triangle, maybe I'll highlight it here in this color, in sort of red, and I'll draw it larger over here. So let's see. Okay, so if we think about that triangle, we know that the base in terms of t will be half of t, since I'm just looking at half of that total width, total track width. So this would be t over 2. This is 30 degrees, and this is h. So the tan of 30 degrees is equivalent to opposite over adjacent. So h would be equivalent to 1/2 of t times the tan of 30 degrees. So hope you can see that where that's what h is equivalent to. And now we can plug this in for here, and we'll see our cancellation of our t's. So theta critical is tan inverse of t over 2 times 1/2 of t times tan 30. We actually get some nice cancellations here. So the 2 and the half will cancel. 2 times half is just 1. T will cancel there. So we're getting the tan inverse of 1 over tan of 30 degrees. And that would be our critical angle. So let's go ahead and plug that, work that out in Excel. I'm getting 60 degrees. Okay. All right. So that's our choice D. Okay. Okay. I think there's a slightly easier way to do that. Now that I think about it, but if this problem to come up, I want to sort of address it at least this way. This is what I sort of was thinking about when I wrote the question originally. But you could also, if it were to rotate about this particular point, that would be again an easier way to do this problem. I draw green and then think about this angle here. This will be equivalent to theta critical. We know that this is 30, this is 30, and this is 30, and 30 and 30 is 60. So that would be another way, of course, of solving it, probably much shorter, but just in case there is a problem that is linked, of course, to the definition of the critical angle, I also wanted to sort of work through this particular definition. Is sort of what I'd planned, at least when I wrote the question. Okay, question 18. A 2.5 kilogram block is attached to a spring on a 20-degree frictionless incline as shown. At the instance shown, the spring is compressed a distance of 3 centimeters and the acceleration of the block is 1.9 meters per second squared in a direction up the incline. Determine the spring constant. So this is sort of a case of where I sort of caution that I typically will not ask a Hookes Law question just for Hookes Law. I will ask a Hookes Law question in the context of some other physics or some other context. So this is basically combining Hookes Law into a lot of prior material about Newton's second law and inclined planes and vector decomposition and so on. So if I think about a free body diagram for the block, I draw something somewhat rough. So I know there's a weight force acting here at the center of mass. A component of that force is in the direction down the incline, which is the part of mg sine theta. And then there is a spring force pointing up the ramp, acting at this particular point here. So this is F spring, and then we know that's equal to K delta L from Hooke's Law. And the sum of those two forces will basically be the net force on the block parallel to the ramp, because I know, as I'm saying here, the track is frictionless, so there's no other forces parallel to the incline. So we can set up a Newton's second law equation to sort of help us solve for the spring constant. So this is an F net equals MA problem. F net, I'm going to call up the ramp the positive direction. So I've got a K delta L force. Alright, something going on with my pen here. K delta L minus mg sine theta, that's the weight force down the ramp, equals ma up the ramp. And I've got to solve for the only unknown. I've got the delta L of 3 centimeters, convert that. I've got the mass of the block, I've got g, I've got the angle, I've got the mass, we've got the acceleration, and its direction is up the incline, so that means that the acceleration is positive. So k will be equal to ma plus mg sine theta divided by delta L, which we can take that m out. So we have a plus g sine theta, all divided by delta L, making sure your delta L is in meters. And we should be able then to solve for the k, so just give me a second to solve for this. It's 20-degree angle. So we got the mass of 2.5 times a of 1.9 plus 9.8 times the sine of 20. And we're going to then take all of that and divide it by the 0.03 centimeters, and I get 438 Newton meters. So choice C as the correct answer. Okay, all right, so that's 18. Do 2 more for this video. Okay, so this question is, you've seen one of these in the we're moving on to stress and strain, and this question looks very, very similar to one of the clicker questions on guitar strings. I think actually it's almost word for word. I think I just copy and pasted the clicker question and just change some of the details, I think, if it's not almost identical. Okay, so let's work through it. But suppose that you have 2 guitar strings made of identical material. However, guitar string is half the width and half the length of guitar string B. When a force F is applied to string A, it is known to extend by delta L. What force would be needed to apply to string B such that it also extends by delta L? So yeah, very, very similar. Okay, so this is a stress strain question. So looking at F over A equals Young's modulus times delta L over L. Okay, so we know that this is some radius R and some length L. B is twice it's half the width and half the length. Okay, so it's 2 L's in length, and it's going to be 2 R's in width. So we're told that when a force is applied to string A, it's known to extend by delta L. And what force we need to apply to B such that it also extends by delta L. Okay, so if we think about rearranging this equation in terms of force, so when a force F is applied to string A, so I'm going to rearrange this for F will be equivalent to Y. Both will have the same Y, and they're going to have both have the same delta L's, and then times area of A divided by LA. So just rearrange the equation in terms of force, and written it in terms of for F, that when we apply a force F to string A, it has some Young's modulus that both of them have the same, so YA equals YB. and they're both undergoing the same delta L. That's part of the question. The question wants to know what force would be needed for to get the same delta L. So delta LA equals delta LB, I guess just equals delta L, and I just equals this equals to Y. For they have the same, but what's different is the areas, cross-sectional areas, and the lengths. So FB will be equal to Y for some delta L. The area of B, since it has twice the radius, it's a cylindrical guitar string, it would have 4 times the area, so 4 times AA. So area of B is 4 times the area of A. Area is pi r squared. So if you double the radius, you get 4 times the area. And then it has twice the length. So then 4 over 2 is equivalent to 2. So 2y delta L, area A over LA. And then the quantity here in parentheses is what we previously defined up there as just F. So 2 F's. So go ahead and highlight, so that's choice B. Okay, that's question 19. So I'll do 20 and then wrap up this video. Okay. Alright, so the graph on the right shows we're moving into momentum at this point. It's a force time graph moving into chapter 9, impulse momentum. The graph on the right shows a simplified plot of the net force on a 1 gram grasshopper as it jumps. Assume the grasshopper is at rest at t equals 15 milliseconds. What is the grasshopper's, and there should be an apostrophe, grasshopper's speed at t equals 55 milliseconds. Okay, so it's a force, time curve, the area underneath the curve is the impulse. So area equals the impulse, and impulse equals delta P. So this is an impulse equals the change in momentum question, where this is going to be area and this is going to be m delta V. So we're looking for the grasshopper's speed at 55 milliseconds, where it sort of begins to sort of leave the ground. So what we can do is find the area as 1/2 of the base, which would be 55 milliseconds minus 15 milliseconds, which is 40 milliseconds. So 10 to the minus 3 seconds, times the perpendicular height of 0.08 newtons. So what I'm doing there is half the base equals, 1/2 the base times the perpendicular height is the area of a triangle. I'm just going to move this down here, so just write out full. And then we can write this as m times Vf minus Vi, but we know that the grasshopper is initially at rest, so they don't have an initial speed. And so we're trying to find the final velocity. So the final velocity will be equal to, again, the 40 by 10 to the minus 3 seconds times 0.08 newtons. I'll put the half down here, times divided by the mass of 0.01 kilograms. 0.001. And we should be good. Okay, so let me work that out. Okay, so 40 by 10 to the minus 3, that's the time interval. 0.08 newtons F max. Divide that by 2 times 1 gram. And I get 1.6 meters per second. That gives us choice B. That's the correct answer. So yeah, impulse momentum question, linking sort of to area under the curve. We've done a sort of similar question, I believe. I hope sort of one of the clearer questions, certainly highlighting the fact that the impulse is the area underneath the net force time graph. Remembering that the time is in milliseconds, noting that the grasshopper is at rest at the beginning, And yeah, from that point, being careful with your algebra. Okay, so that's 20. I will then follow up another video on questions 21 to 25.